Right, hi guys, and welcome back to a brand new video. It's been way too long since I made one of these, and I'm very excited to start this project. So you probably heard me talk about socket programming before, or network programming, something that I wanted to do. The last series that I made, I enjoyed so much. It was creating a Alexa in C. And I just wanted to start a new series. So I thought, well, I'm just going to go through Beej's Guide to Network Programming. Some of you may have heard of it, some of you may not have heard of it. Talked about it before. It's something I want to do for a while. I have no clue what network programming is, so I'm a beginner, which is great for someone like you if you're watching this and you're a beginner too. So Brian, Beej, Jorgensen, Hall, he has created some marvelous resources on learning C from scratch, or from, if you're a beginner. So please go look at his guides. They're fantastic. And what my plan is to effectively read them on camera. They're free, they're accessible. I'll put a link to it in the description. And I'm going to kind of go through the tutorial. It's more of a tutorial. It's not really like I'm not going to be writing my own code here. I'm just going to be kind of copying what he said. Things are going to go wrong. That's fine. We'll figure it out. We'll troubleshoot after. But yeah, that's what we're going to do. For all the 260 or 256 subscribers that I've got, thank you very much. We're a quarter of the way to 1,000 subscribers, so please drop a comment, subscribe. I like hearing all your experiences about learning C, and I'm hoping that we can provide a community for people who want to learn C from scratch. So let's get into it then, okay? It's going to be probably a bit boring unless you just want to hear me rant about things. But, I'll put chapters in if you just want to skip straight to a particular chapter, okay? But we're going to look at this together, okay? So first, hey, socket programming got you down. Is this stuff just a little too difficult to figure out from the man pages? Now, hopefully you're all familiar with what the man pages are. If you're new to this channel, you're probably not. So the man pages, I'm doing all my programming in the terminal, okay? Now, if you're a beginner to C, if you're a beginner to programming, you don't have to do that. You can use Visual Studio, you can use Visual Studio Code. There's a lot of different IDEs out there that you can use. I've got a ghosty terminal emulator running on my Mac, okay? And that makes a difference as well if you're using Windows, but we'll get into that shortly. But quite literally, if you've got a terminal and you're programming in your terminal, I'm going to be using Vim or NeoVim, okay, to do my programming, just because I find that that's what's easiest for me. You can literally write all of the code in whatever IDE you want to use, okay? So the man pages then, if you type in the man or the manual pages effectively just give you documentation on everything that you need to know about C programming or any of the system calls we're going to be using. We'll get into system calls shortly. Anything that you need to know, you can use the man pages for, and they're really, really useful. They're also difficult to read sometimes, not really. I mean, this is something that somebody talked about before, one of the early subscribers, that you can type in man, and they'll go over the manual pages, what they are. So you can effectively go over the different options, and it gives you a bit of a walkthrough of what they are. Now, again, if you're going to be an excellent programmer, it's good to read the documentation. I'm lazy. I don't do that often, but, I would encourage you to do that. But it's really interesting. There's a lot of good information in there. There's a lot of a big wealth of information in there. Okay, so to leave that, just press Q, and you've left that. That's fantastic. Right, so you want to do the call internet programming. That's what socket programming, network programming is, allowing devices to communicate over a network. But you don't have time to wade through a gob of structs, trying to figure out if you have to call bind before you call connect, etc., etc. Well, guess what? I've already done the nasty business, and I'm dying to share the information with everyone. You've come to the right place. This document should give the average competent C programmer the edge she or he needs to get a grip on this networking noise. Now, competent C programmer, I haven't touched C in over 2 months now, so I'm hoping that some of this will make sense. I'm going to make some stupid mistakes, I guarantee that, but we'll work through it. It's fine. We can troubleshoot. We've got AI on our side. I'm going to try and stay away from using it as much as possible, but if I have to troubleshoot, it's always good to go to AI, okay? I know people will hate me for that, but it's just my personal take. I think the thing with vibe coding is that quite literally, I think vibe coding from scratch is a stupid idea, and I think you're never going to learn a language or something very well. But if you just made an honest mistake, a simple mistake that you can't figure out and you're banging it up against the wall, AI is a good tool to just speed up the learning process there and catch the errors you've made. That's my personal take. That's a hot topic. We'll get into that another day. Right, check it out. I finally caught up with the future, just in the nick of time too, and we have updated the guide for IP version 6. Now, right, let's talk a little bit about the definitions really quickly. If you're new to networking, I haven't done any networking in a long while. An IP address is quite literally the location of your machine on a particular network. Okay, so every machine on your network in your house will have a IP address associated with it, an IP address associated with it. Okay, now you can type commands into the terminal to figure this out. You don't need to, but quite literally that is where your IP address is, so the location on the network in your house. Okay, and each of your devices will have a MAC address which is completely unique to that machine. Okay, that's how data is transmitted via the MAC address. Okay, right, so that's clear. A port then, okay, a port is also important to know, and you probably heard of ports if you've done any sort of web programming before, maybe not the low level stuff that we're going to go through this guide, but effectively a port is the service or the processes that are running on that particular machine. And then a socket then is effectively the interface that is allowing the communication between the devices. Okay, and I believe, again, this is like, I've done a little bit of research on it, but going back a while ago, okay, I've made some notes on it as well, but quite literally, as I understand it, the socket address then is the IP address plus the port, which makes sense because I've done a little bit of HTML programming, but it's like high level stuff, and I don't really, again, I'm not really in depth, you know, with the low level stuff, so I may be wrong on that. Okay, let's go through this a little bit, and then we'll move on to the actual definitions and such like that in a bit more detail. Right, so this guide then is been written as a tutorial, which is good. Again, it's not going to be something that we're going to create our own code on. It's probably the best when read by individuals who are just starting out with socket programming and looking for a foothold. Certainly not the complete and total guide for sockets programming by any means. Hopefully, though, it'll be enough of those man pages to start making sense. That's fantastic. And then it goes on to saying that this has been done with GNU's GCC compiler. Now, for those of you who probably are using Windows, maybe best to just set up a VM using Ubuntu or something like that, because it's given a bit of a guide. You can use it with Windows. You can use Windows Subsystem for Linux. That might be a better idea, actually. But read that if you want more details on it. Okay. So email policy, mirroring, notes for translators, copyright. Hopefully I'm not breaking any rules by showing this on the screen. Again, it is free. Okay, so that's it. That's effectively the first chapter. So let's go into effectively what is socket programming and what is a socket. So you hear the talks of sockets all the time, and perhaps you're wondering just what they are exactly. Well, they're this: a way to speak to other programs, using standard Unix file descriptors. What? Okay, you may have heard some Unix hackers state, geez, everything in Unix is a file. That's true. We've all heard that, surely. Okay. What that person may have been talking about is the fact that when Unix programs do any sort of input-output, they do it by reading or writing a file descriptor. A file descriptor is simply an integer associated with an open file. But, and here's the catch, that file can be a network connection. So a FIFO, first in, first out, a pipe, a terminal, a real on-disk file, or just about anything else. Everything in Unix is a file. So when you want to, I'll zoom in a bit as well, when you want to communicate with another program over the internet, you're going to do it through a file descriptor. You better believe it. Where do I get this file descriptor for network communication, Smarty Pants? This Smarty Pants is probably the last question on your mind right now, but I'm going to answer it anyway. You make a call to the socket system routine. It returns the socket descriptor, and you can communicate through it using a specialized send and receive. So these are system calls, I believe. That would make sense. And for those of you who don't know what a system call is, it's effectively a bit of code that is going to interact with the hardware, and the operating system doesn't want to give. So effectively, it's just you call it's almost like a function, but it's providing some unique operation that you wouldn't want to give a person access to effectively. Okay, so you call the system call. It effectively executes or it puts you into kernel mode, a privileged mode, and then does something fancy, and then it has a return from trap instruction, which takes you back then to the user. I don't know if I explained that well. I don't know if I explained that well at all. Maybe I should get a diagram up. Hang on a second. Right, okay, so this probably explains it best, okay? This is when the operating system's at boot, and this is what the hardware is doing. So we initialize a trap table, and what the hardware will do is remember the addresses of all the system call handlers. Then when we're, the operating system is running, so when it's at runtime, what it'll do is it'll create an entry for process list, allocate memory for programs, load program into memory, set up the user stack with args. Don't worry about the specific details here, okay? Effectively, when we're running a program, that program may call a system call, which would look something like socket, send or receive. And then what happens is the hardware is going to save the registers to the kernel stack. It's going to move into kernel mode. It's going to handle the system call. Then it's going to effectively restore the registers of this program that is running. And then effectively we are back to the main program. So it sounds like it's not important, but it's really important to have an understanding of that if you get into C programming, because you need to have an understanding of what the computer is doing from a low level. You need to understand what system calls are, why they're important. And the reason why they're important is because they're often doing something privileged or something that we wouldn't want to give something access to. And OSTP goes into that in great detail. OSTP is a fantastic book, which I would encourage you reading. Anyway, back to the video. But hey, you might be exclaiming right about now, if it's a file descriptor, why in the name of Neptune can I just use a normal read and write calls to communicate through the socket? The short answer is you can. The long answer is you can, but send and receive offer much greater control over your data transmission. Okay, so they're specific to network programming, they're specific to what we need to do in that particular context. Sounds about right to me? That's fine. So what next? How about this? There are all kinds of sockets. There are DARPA internet addresses, internet sockets, path names on a local node, Unix sockets. It's just so confusing. This is the thing with networking. This is the thing with network programming. There's just so many protocols and fancy names for things. It can look a bit daunting, but I'm sure it's not as complex as it looks. Anyway, CCI TT X.25 addresses. X.25 address sockets that you can safely ignore, thank God for that. And probably many others depending on which Unix flavor you run. This document deals only with the first internet sockets. Whew, okay, we got lucky there. So there are DARPA internet addresses and internet sockets, and that's what we're going to focus on. Great. Awesome. Okay, that sounds pretty clear. So 2 types of internet sockets. So what's this? There are 2 types of internet sockets. Yes, well, no, I'm lying. There are more, but I didn't want to scare you. I'm only going to talk about 2 types here, except for this sentence, where I'm going to tell you that raw sockets are also very powerful, and you should lock them up. All right. Already, what are the 2 types? One is stream sockets, which isn't that where data just gets effectively... Oh, I don't know. I'm not going to act like I know. Right. So stream sockets. The other is datagram sockets. Which may hereafter be referred to as sock stream and sock dgram. Okay, so datagram and sock stream. So socket stream, socket datagram, respectively. Datagram sockets are sometimes called connectionless sockets, though they can be connected if you really want. See connect below. Stream sockets are reliable, 2-way connected communication streams. If you output 2 items into the socket in the order 1, 2, they will arrive in the order 1, 2 at the opposite end. They will also be error-free. I'm so certain, in fact, they will be error-free that I'm just going to put my fingers in my ears and chant la 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 if anyone tries to claim otherwise. Right, okay. So stream sockets are highly accurate, reliable, 2-way communication. That sounds about right. That's what I had in my head, but I didn't want to act like I know and make a fool of myself on this video. So, right, that's fine. So, what uses stream sockets? Well, you may have heard of the Telnet or SSH applications. Yes, they use stream sockets. All the characters you type need to arrive in the same order that you type them. Right. Also, web browsers use the Hypertext Transfer Protocol, HTTP, of course, which uses the stream sockets to get pages. Indeed, if you telnet to a website on port 80 and type get HTTP 1.0 and hit return twice, it'll dump the HTML back at you. If you don't have Telnet installed and you don't want to install it, or your Telnet is being picky about connecting to clients, the guide comes with Telnet, like program. This should work well for all the needs of this guide. Note that Telnet is actually a spec networking protocol, and Telnet doesn't implement this protocol. Okay, so I mean, I'm not gonna. Should I do that? Okay, let's have a look at that. Right, okay, let's have a look at doing that. So I think we'll have to do brew install telnet. So while that's installing, let's just carry on. Right, so how do stream sockets achieve this high level of data transmission quality? They use a protocol, let me guess, TCP. Didn't even look at the screen. I mean, I kind of am, but I know the TCP is more reliable. So, right, so they use a protocol called TCP. Now, a protocol, for those of you who don't know, it's an agreed set of terms that that effectively allow us to keep different devices to communicate. So it's effectively a set of rules that allow many different devices to communicate with each other. So the Transmission Control Protocol, otherwise known as TCP, for extremely detailed info on TCP. TCP makes sure your data arrives sequentially and error-free. You may have heard of TCP before as the better half of TCP/IP, where IP stands for Internet Protocol. IP deals primarily with internet routing and is not generally responsible for data integrity. So that's interesting, because I always just assume TCP is TCP/IP, but no, have I just said something really stupid? You may have heard of TCP before, as it is the better half of TCP/IP. Okay, I didn't know if TCP was on its own. I just assumed that TCP/IP is just I just assumed that people say TCP shorter for TCP/IP. Okay, this is done. I'm just gonna save myself from rambling. So right, we'll clear that. What did it ask us to do? So if you telnet, so I believe what we do is telnet google.com 80. Okay, and what did it ask us to do? So escape character. So it said, can I just copy this? Let's try that. Oh. There we are. Okay, so I pressed enter twice and it provides me with the HTML. So what was the purpose of that again? I forget. So so what uses stream sockets? Well, you may have heard the telnet or SSH. So SSH as well, secure shell, for those of you who don't know. That allows you to effectively access another device's terminal through your own terminal. So if you type in SSH and then the IP address of a device you want to secure shell into, then you can do that. But before I carry on, I got to sort of what I was thinking about. Right, okay, so I have to look this up, but I'm not ashamed that I have to look this up, because I'm sure a lot of people didn't know as well. Okay, so TCP is just the protocol that allows the devices to communicate with each other at the transport layer, I believe, is it? So, no, sorry, I got that wrong. So operates at the transport layer to ensure data is traveled error-free in order and reliably, whereas IP then is at the network level, and the combination of TCP/IP is the full suite that allows internet communication. So I thought that was worth looking up. Again, a bit embarrassed I didn't know that, but okay, it's fine. We just assumed that they were both the same thing. So IP deals primarily then with internet routing and is generally responsible for data integrity. Cool. What about datagram sockets? Why are they called connectionless? So I'm guessing that they're unreliable and it's to do with UDP. And there's a bit of a spoiler because I think it says W, so that's fine. So why then, Robert? Well, here are some facts. If you send a datagram, it may arrive out of order. If it arrives, the data within the packet will be error-free. Okay, right, that's interesting. Datagram sockets are also use IP for routing, but they don't use TCP. They use user datagram protocol, of course, UDP. Why are they connectionless? Well, basically, it's because you don't have to maintain an open connection as you do with stream sockets. You can just build a packet, slap an IP header on it with destination information and send it out. No connection needed. They are generally used either when a TCP stack is unavailable or when a few drop packets here and there don't mean the end of the universe. Yeah, okay. Sample applications then, TFTP, so trivial file transfer protocol, a little brother to FTP. Why, like, again, why are there so many acronyms? It's just TCP, TFTP. It's just annoying. Anyway, multiplayer games, streaming audio, video conferencing, etc. Wait a minute, TFTP and DHCP-CD are used to transfer binary applications from one host to another. Data can't be lost if you expect the application can't be lost if you expect the application to work when it arrives. What kind of dark magic is this? It is quite mind-boggling though when you think about it. Like, I was speaking to somebody about it the other day where we could be on one side of the world. I'm in the UK. Somebody could be in America. And we could be versing each other on a game, let's say Call of Duty. The fact that that data is being quite literally transmitted to that person in real time is quite mind-boggling. Fiber optic is insane. It's absolutely crazy. So wait a minute. Did I read this? Yeah, I did. Well, my human friend, TFTP and similar applications have their own protocol on top of UDP. For example, the TFTP protocol says that for each packet that gets sent, the recipient has to send back a packet that says, I got it, an ACK packet. If the sender of the original packet gets no reply in, say, 5 seconds, he'll retransmit the packet until he finally gets an ACK. This acknowledgement procedure is very important when implementing reliable SOC datagram applications. Okay, so that's interesting. So quite literally, it keeps on sending it. If they say, yes, we got it, fantastic. If not, then it'll keep on trying to transmit it. After 5 seconds, I'm sure that's just something that they're just using as an example. I don't know if it would be a standard 5 seconds. I'm not sure. But anyway, that's interesting. So for unreliable applications like games, audio, or video, you can just ignore the drop packets or perhaps try to cleverly compensate for them. Quake players will know the manifestation of this effect by the technical term accursed lag. The word accursed in this case represents any extremely profane utterance. So that's quite interesting. Right, first of all, I've never played Quake. That's not the interesting part, but it's good that there are. I've heard that. I know that. I have an understanding of why there are two different, kind of protocols for sending data across the internet. But that it's made very clear. But there, the fact that we have TCP/IP for effectively, I would say, mission critical communication. I don't know if that's a bit over dramatic, but then for reliable applications, let's say, and then for unreliable applications like games, audio, and such like that, we can use datagram now, which is quite interesting. But yeah, that's fine. So why would you use an unreliable underlying protocol? Speed. I knew it was going to be speed. See, I can't, because I'm reading it, I can't make the guesses. But anyway, two reasons: speed and speed. So of course, TCP/IP then comes with the fact that it's going to be much slower because it puts so much emphasis on being reliable. So it's way faster to fire and forget than it is to keep track of what has arrived safely and make sure it's in order and all that. If you're sending chat messages, TCP is great. If you're sending 40 positional updates per second of the players in the world, maybe it doesn't matter so much if one or two get dropped, and UDP is a good choice. So it's very interesting. I quite like this guide so far. It's breaking things down nice, simple, in a concise way. So that's great. Right, so low-level nonsense and network theory. So we haven't got much left of this section. I think I'm probably going to leave it there because we are probably about 20 minutes into this video now when we have done any programming. So this will be a little teaser for you guys. Again, next episode we will do some programming, I'm sure of it. Low-level nonsense and network theory. So since I mentioned layering of protocols, it is time to talk about how networks really work and to show some examples of how SOC datagram packets are built practically. You can probably skip the section. It's good background, however. Okay, so this is something that I know for a fact I need to get better at networking. I need to have a good understanding of these, of TCP and UDP, because the general idea, again, I suppose when you have that little refresh and the fact that UDP is more unreliable, but it's faster, and TCP is more reliable, it sounds familiar to me, but again, understanding this more deeper, lower level is probably more important, okay? So, hey kids, it's time to learn about data encapsulation. This is very, very important. It's so important that you might just learn about it if you take the network course here at Chico State, okay? So go do that network course at Chico State. if you're, I don't know where Chico State is. Is it Chicago? I have no clue. But anyway, go do that course. Basically, it says this, a packet is born, the packet is wrapped or encapsulated in a header and rarely a footer. By the first protocol, say the TFTP protocol, then the whole thing, TFTP header included, is encapsulated again by the next protocol, say UDP. Then again by the next IP, and then again by the final protocol on the hardware, physical layer, say Ethernet. Right, okay. So we have our data, which is encapsulated by the TFTP, then the UDP, then the IP, and then the Ethernet. Okay, that makes sense. When another computer receives the packet, the hardware strips the Ethernet header. So the kernel will strip the IP and UDP headers. The TFTP program, a TFTP program strips the TFTP header, and it finally has the data. So now I can finally talk about the infamous layered network model, aka ISO OSI. Okay, so again, I've heard of this, but don't know in great detail, so let's have a little look. So, right. So this network model describes a system of network functionality, has many advantages. Describes a system of network functionality that has many advantages over other models. For instance, you can write socket programs that are exactly the same without caring how data is physically transmitted. So if it's by serial, if it's by Ethernet, AUI, or whatever, because programs on a lower level deal with it for you. So the actual network hardware and topology is transparent to the socket programmer. Without any further ado, I'll present layers of the full-blown model. Again, this is all familiar to me. I studied this in university, but we're going back years ago now, so it's all a bit wishy-washy. So we have to remember, so application, presentation, so these are different layers in OSI, I believe, is it? So the physical layer is the hardware. So that is your serial, your Ethernet, etc. The application layer is about as far from the physical layer as you can imagine. It's the place where the user interacts with the network. So this is where the user is interacting. This is the actual hardware, so whatever our device is connected up to on the network. Now, this model is so general that you could probably use it as an automobile repair guide if you really wanted to. This model is so general that you could probably use it as an automobile. Okay. A layered model more consistent with Unix might be the application layer. So your telnet, your FTP, etc. Host-to-host transfer protocol, so your TCP, UDP. Internet layer, so that's your IP and routing, and your network access layer, so Ethernet. So this is something that effectively, this is how we would recognize it then. Okay, so we have an application layer, which is the thing that we're interacting with. We have the protocol that we are using to connect to the network, IP and routing, and then our Ethernet or Wi-Fi or whatever is connecting us on the network. Sounds about right. Okay. At this point in time, you can probably see how these layers correspond to the encapsulation of the original data. See how much work that is in building a simple packet. Geez, and you have to type in the packet headers yourself using cat. Just kidding. All you have to do is stream sockets to send the data out. All you have to do for datagram sockets is encapsulate the packet in the method of your choosing and send it out. Okay. Kernel builds the transport layer and internet layer on for you, and the hardware does the network access layer, our modern technology. Again, so system calls are going to be doing a lot of this work for us then. So see, I told you it's important that you learn about system calls, so make sure you do that. Okay. So ends of our brief array into network theory. Oh yes, I forgot to tell you everything I wanted to about routing. Nothing. That's right. I'm not going to talk about it at all. The router strips the packet to the IP header, consults it to the routing table, blah, blah, blah. Check out the IP RFC. Let's have a look at this. Okay, is this... Okay, this is something that I'm going to read in my own time. Will I actually read it all? We'll see. But I hope to read that all. So I won't bore you with that. I'm not going to go over that, but something that I should look at. If you never learn about it, well, you'll live. Okay, so that's good. So again, I guess some of this, again, we're going to pick up this in the next video. So apologies if you've watched this and you've been wanting to see some programming. We haven't. done any, but it's fine. I'm sure we are. We've got another section which is probably going to be a lot of reading, but after that I think is when, oh no, there's a bit of programming in here. That's great. So yeah, I think, you know, I think with a lot of this, I mean, you probably don't need to become an expert in it to just understand the basics. And I think, in all honesty, I mean, you could probably get away with just learning the bare minimum, but I think, you know, for the sake, if I'm really keen about learning this, I really should read that. So I'm going to read that. But anyway, we're going to leave it at that. So apologies if you think this video has been a bit boring, because it probably has been. It's been fun for me, but I don't know if you guys are interested in this. So let me know what you think. If you just enjoy me reading through this, I'm happy to carry on. Read this book. If you take anything from this video, read OSTEP, Operating Systems in 3 Easy Pieces. Yeah, you can see that I think I talked about this, didn't I? Yeah, I did. Okay. Thank you for watching. Hopefully you'll enjoy the next episode where we're going to do a bit of programming. If you've got any questions, leave them in the comment section below. But please refer to this guide because it is what I'm using to kind of cover this. So thank you for watching, and I'll see you in the next one.